Hi again. So this is the third video from the series that we've been looking at, and this video is focused on sketching composite functions. So I'll just neat it up. So we're talking about composite functions. So the steps are a little bit different, but something that we do want to consider. So what we're going to do is we're going to write the function as a single function, have a look at it, and think about how it might be sketched. We're going to consider the domain where the function is defined. Then we're going to find points uh, including the intercepts, asymptotes, and stationary points. We all know how to do that. And then we're going to consider the curvature of the graph. So one thing that we have to remember though is this definition when we're dealing with composite function, and that is if I have a function of f of g, okay, written as f of gx, is defined where the range of g is a subset of the domain of f. I want us to also note that if this is true, we accept the domain of g as the domain of f of g. All right, so let's get into it. So what we're going to look at is we're going to look at the first example. So if fx equals x squared plus 1 and gx equals 1 on x, consider sketching y equals fgx. So simply speaking, we're going to write this as a single function first up. So a single function for this is going to be y equals fgx. We're going to substitute gx into fx. So I've got 1 on x all squared plus 1. And this can be written as 1 on x squared plus 1. Having a look at the function, we can already see that this is going to be a truncus with a translation of 1 unit upwards. I am going to consider my domain though. Okay. And I'm going to construct the table. So let us construct our table. Domain, range, f and g. It's always important when dealing with composite functions to construct these types of tables because you want to make sure that you're really adhering to that rule that the range of G is a subset of the domain of F. And what we're going to do is we're going to put in here, first thing that we're going to put in is our domain of F. So the domain of F is, let me just think about your brackets. I like to use the domain in this form. Okay, the range will be 1 to infinity. Okay, then I'm going to think about the domain of G. Okay, so this will be negative infinity to 0 in union with 0 to infinity. Apologies for trying to fit it in. And likewise, the domain of this will be negative infinity to 0 in union with 0 to infinity. Now, the key question that I'm asking here is, does this domain, so this domain, does this range of G fit into this domain of F? Okay, so I can see that it does fit within there. Okay, so I can say that the range of G fits into the domain of F, and therefore, importantly, When I talk about, when we discuss the domain of the composite function, we can accept the domain of G as the domain of the composite function. So I'll just give a big tick for that. All right. So next step is we're going to have a look at our y-intercept. X equals 0. Okay. 1 on 0 squared plus 1. Okay. Undefined. We're going to consider our x-intercept. Y equals 0. And we're going to have 0 equals 1 on x squared plus 1. This in turn is going to give us x squared equaling -1, and not x squared, but x then equals the square root of -1. So there are imaginary solutions to this, but no real solutions that we want to consider. Okay, we're going to look at our asymptotes. And with our asymptotes, we can clearly see that there's an asymptote at x equals 0. We can also note that there's an asymptote at y equals 1. We can consider our stationary points. And with our stationary points, we're going to say f dash of gx. Now, we might use a chain rule to be able to use this, but we're going to say that equals 0. And we're going to say no stationary points in relation to this. I'm going to return to the equation that, or the function that I had, that 1 equals x squared plus 1. Knowing the methods that I know, I can safely construct the graph with some key knowledge. Okay, so I can say here, I've got an asymptote. Let's put our asymptotes in. So I have an asymptote there, and I also have an asymptote running this direction. So I'm going to say y equals 1, x equals 0. I can see here that it's a function with a truncus form. Therefore, I can get a sketch. It looks like that. And that gives me a clear sketch of the composite function. Okay, moving to the next sketch. So if fx equals sine x and gx equals e to the x, sketch y equals gfx. So what I'm going to say here is I'm going to write my single function. And with my single function, I'm going to write that as y equals e to the power of sine x. Okay, very important. And I'm going to have a look at my domain. So the domain that's going to be produced from this. Okay, so I'm going to start with f. Actually, put my domain here, my range here, f and g. Let's start establishing to see if it's going to exist. Okay, so let's start with our domain of f. So we know that that's going to be between negative infinity to infinity. Our range, though, is going to be between -1 and 1. Domain of g is going to be between negative infinity to infinity. And the range of G is going to be 0 to infinity. Okay, and I'm asking, does the range of G fit into the domain of F? So does this range fit in this range here? I can safely say that it does, which is great, which means I accept the domain of G without any restrictions as the domain of y equals sine x. Okay, so I can say range of G is a subset of the domain of F. Okay, and this will be my domain of y equals e sine x, this region here. Okay, let's have a look at our y-intercept. X equals 0, and what I'm going to have is e equals sine to the 0. This equals e to the 0, which equals 1. Our x-intercepts, we're going to have y equals 0, and we're going to look at 0 equals e to the sine x. Okay, what I would do if I'm dealing with this is log e to the 0 equals sine x. Just want to note that log e to the 0 is undefined, therefore this does not exist. I'm next going to consider my asymptotes. I can't find any asymptotes, so I have none. Then I'm going to consider my stationary points. And with my stationary points, I'm going to consider f dash gx equaling 0. And this gives a general solution of 2n minus 1, all in brackets, times pi over 2. That's handy information to have. I'm now going to go into sketching my graph. I might actually do the graph on this page. Okay, I'm going to note that there's no x-intercepts, and I'm going to note that there's going to be some positive values. Once finding my stationary points, I have to note where they're going to exist. I'm going to note that I have, for the value, I'm going to have it existing between e to the 1 and e to the negative 1, y negative 1 and 1, because sine x can only exist between negative 1 and 1 as a range. All right, and then I'm going to start putting some points in. I might scatter these points just a little further. Okay, and I know from how the graph would work with my sketch. I'll start sketching it in red. Here's we get curves. That's going to be oscillating. Probably the last curve, I'll probably just straighten up a little bit. Okay, and there's my sketch of HX. So that's what HX, or we haven't called it HX, so I apologize. We call that Y. That's it for today. I hope this has helped.